Okay. So yeah, we were in the first example here. So now we can do the same with yeah, so if I get the result I had on my laptop, so it's 374 microseconds to compute the three kernels. So no, it's not good or bad, it's just a reference that we have. And then we can do the same, but switch on CUDA, and we will see what we can do. So if I put this here, I don't know, Tom, can you be more precise? Well, once you say oh yeah, maybe. Oh yeah, I think I get it. Check this one. Well, you should be here and you start stuff. And here you need. No, you don't need. Tom, I'm pretty sure you didn't get the examples, but the full lecture, and you don't want the full lecture. You just want the examples. And in the example, you don't need anything. So get the targz. Yeah, I was putting a new command here, and then we can profile the first CUDA example that we had here. So once you done that, you can get this one, and we can have a new profiling. So for now, we get 374 microseconds for the three kernels in the NVC++ examples. And we'll do the same with CUDA. So enable CUDA yes and enable NVCPP no, and GPU mode yes. And we'll compile this one. So we'll check this one. So I put it in the chat here. And normally, if you have the Laplacian CUDA, where is my Laplacian? This one? No. Yes, this one. Yeah, this one. So if you are a bit late, you have all the command in the chat, if you in the stream, if you want to check. So the idea here is we have a reference, so NVC++ with 374 microseconds for the to compute the three kernels, and we'll check the first Gray Scott Laplacian example in CUDA, and we profile it to see what's going on. And of course, it will be bad, but the point is to understand why and to improve it. So And normally should be, yeah, should be quite okay.
Sorry, once we have the sorry, I forgot the name about the profile that we have. Once we have this file, how can we open it to have the same view as you? Sorry,
here
I
it's
didn't get
better
that.
to, in fact, you are obliged, I think. Maybe if you forward X on your SSH, but I'm not sure it's a good idea. If you have Nsight, just Nsight, it's a package, so you can just install Nsight. It's 300 megabytes, something like that, and then you can get the report and get this nice view. So be sure that to have, so it's Nsight 2025.3. So it's the last one available in the CUDA HPC, the SPC SDK 2025.5. It's not the 5.3. And if you get this one, normally you can have this view. So you can explore, you can check, you get the speculative prefetch. And here, with this example, you will see that we have the classical CUDA memcopy because it's a CUDA program. So we do our CUDA memcopy. Then we start our kernel without losing performances because the data are already on the GPU. And then we have, as before, the kernel, the Laplacian kernel. Here, so all this type of Laplacian kernel. And here I get the other kernel, of course, for the update, a concentration update of UMV. By the way, if you don't want to be bothered with the naming, report 1, 2, 3, stuff like this, you can use a -O to name the report. So for example, if I take this one, I can say just after profile, of course, before the program, you can say -O and you can say I don't remember the name, of course. It's report NC-strep. Yeah, this one. So you can name the report. You don't have to remember, okay, report 1 is this one, or to rename it after the work. Okay, so maybe we can do that together. So if I get the first one here, so I get 3, I don't remember. Yeah, 374 microseconds to execute the 3 kernels. And if I get this one, I get my kernels, I did my selection to see roughly 970 microseconds. It's a lot. It's really a lot. So 900 here and 300 actually for NVC++. So there is something we are missing. If you can have a look to the two profiling, normally you should notice something in the occupancy. So in the CUDA example, if we look at the kernels, we have an occupancy of 62%. Not that good. And if we compare to NVC++, for the same kernel, we get 100%, which is way better. So there is a trick. So there is a problem. There is a problem here. So theoretical occupancy 100%, and we don't have it. Can you guess what is the problem? Online? So I will help you a bit. In our CUDA example, we get blocks of 30 by 32 element threads. And in NVC++, I used to say a lot, there is only 256. So the NVC++ blocks are way smaller than ours. So what we can do is to say, okay, let's try to keep a block of 256 threads, but in 2 dimensions, because we want to compute in 2 dimensions in our kernel, and adapt the grid above to make it match. So what we can do is to say, okay, I can, here, I have my grid 36, 30, 60, 32, the previous one, and I get a very bad performance. So what I propose you to do is to change a bit this grid first and see what's going on. Because I told you before that the ordering matters. And of course, I give you the wrong ordering because it's an exercise, so it's normal. So you can try in the source, here in the CUDA Laplacian branch field CPP, maybe I can give you the link. Okay, so we'll move a bit on the examples. So okay, so we have almost half an hour, so we'll move on a bit. So if you transpose, or at least if I transpose on my laptop, I get from 975 microseconds to 361 microseconds. So I have the same size of block, but I just transpose the read of the block, and I get more than a speedup of 2, which is a lot. And here you see the error is not that much. It's 30, 32, and 32, 30. And as I explained to you, 32 is the size of the warp, and the warp, so we have a column-wise matrix, because we want to store it in column-wise in PNG, for example. And the block has to be column-wise, even if the whole world of the BLAS is row-wise. And the warp is the x-axis. So I want to have a 32 on my x-axis. And then I get 361 microseconds for this computing. So more than a factor of 2 just by transposition. That's a lot. And it's easy to get lost. Of course, you may have noticed, if you, for those who succeed to launch this test, at some point you will have a problem because you change the size of a block. You say, okay, now I'm column-wise and not row-wise, but the kernel is not updated, and you have a crash, and you don't have error. And you get the CUDA error, and you don't have error, and you get the last CUDA error, and you don't have error, and you don't know why. It's really simple. Once you have a segmentation fault on a GPU, you cannot catch it. If you have an invalid pointer, it's okay. If you have an invalid free, it's okay. But if you have a segmentation fault, just stop. And you have to guess that maybe there is a problem, and the problem is related to a read or write. And in that case, it's really simple. I have my number of columns, which is this one. I multiply by this in my kernel. If you swap the axis, it has this multiplied by this one. So I have this one to the square. Of course, it's too much. And since it's too much, you have a segmentation fault. So you have to update the kernel, and the way is really simple. In fact, here you get the number of columns here, for example, in the I, you take it and you move it to the J, and that's it. It's fixed. So it's already done for all the corrections. So I will not do it right now. We'll have the correction after the lecture. So more than a speed up of 2 for the first part. Now we will move on a bit. So now we have nice defined block shape. So we have the margin of 1 pixel around the image. We have the block, so 60 times 32, it's 1920. Okay, no problem. And now we will try to get our 100% usage. So let's spy a bit what NVC++ does. So here we have 361 microseconds with 62% of usage of theoretical occupancy of the GPU, which is not that good. And on the opposite, so with Nsight, and not the opposite, with NVC++, we get 369 microseconds, so it's a bit slower because there is an overhead, but the occupancy is 100%. And the grid is one-dimensional, and the block is one-dimensional because we have an index of an array of index, so one-dimensional. Yes, Adrien?
Would it be correct to infer for those numbers that NVC++ is more wasteful in the sense that it needs to use more GPU resources to achieve the same execution time?
Yeah. And so, yeah, only more time. So we want to have 2 dimensions and not 1, because in the CUDA kernel we have Y and J, so to have X-axis and Y-axis. And now you know the importance of swap axis, so it's important to have a nice contiguous data once you want to read. Otherwise, you kill your bandwidth. So let's try this one, for example. So maybe we'll pass quickly onto it because, of course, you notice that it's not the right order here. So if I do this one, I get the theoretical occupancy of 100%, but it's 536 microseconds for the 3 steps. And if I do the other one, so 60, 32, so I swap transpose the axis here, I have still the same occupancy in Nsight, but with this transpose, I get 284 microseconds. Way better than NVC++. So generally, I use NVC++ like this. So I try to have a block size, roughly the size I think it's okay. And then I ask NVC++ or Thrust, because they all manage to get the block automatically. And I try to guess why they use this kind of stuff. And of course, NVC++ mainly and Thrust, they use oftenly 256 in terms of the size of block, so mainly in 1 dimension. So we want to do the same, but in 2 dimensions. And you see that the block is really long, in fact, in that case. So 284. So we beat the classic NVC++, but of course, the NVC++ could be better. And maybe now we can do some stream. For example, I'm not sure we'll have time for that, but you can play a bit with the stream. So the classical single execution stream is this one. So 1 stream, the default stream. So the stream 7 normally, where is it? Where's my stream 7? Default stream, the very last one, of course. So this one. Here you get the stream if you want to have a look. And what we can hope is something like that. So we execute Laplacian of u and v at the same time, and then we compute the update of u and v. And we gain a lot by doing that with two-stream execution. So we can say, okay, we have one stream for the Laplacian u and for the update u and v, and one stream for the Laplacian v, and we do a sort of barrier here to be sure that everything is fine and no problem. Can you guess if it's okay for us to use several streams to compute? Or maybe online, if you have an ID. The looker for to control if it runs on the GPU or on the CPU is the parent sec. The dash parent sec equal GPU or parent sec equal CPU. No ID? Okay, so things that we can say is if the Laplacian use less than 50% of the occupancy of the GPU, it's okay for the scheduler. You can use 50% at 50% and no problem. You can execute both at the same time. But if they use more, 62% or 100%, you will have this one and will be very disappointed because you say, okay, I use two streams, but I don't have again, and just lose the time and use this stream. Because the kernel are really efficient. So to make it short here, we are in the more than 50% case. So at the end, it depends. Maybe you are stuck with 60% and you cannot improve. So to gain parallelism, you can decrease a bit the number of threads you start to reach 50% and to start two of them. But here I choose to do the 100% stuff, so we cannot do this one. But very interesting, if you are stuck, you have two options each time. So we're still on time. Oh yeah, computing this transfer. Maybe you can play with that also if you want. Maybe I can show you. So this one is okay, this one is okay. Effective. Oh yeah, this one is okay. Laplacian transpose is okay, and data is okay. Yeah, this one maybe we can play with it a bit later. Oh, no such file or directory G++11. There is no G++11. It's quite annoying, but maybe there is another one. Yeah, with NVCC, I did not mention that, but if I go in my sources somewhere, I think it should be here normally. Yeah, if you go in the CUDA symmetrics.txt, I did G++11 here, hard-coded because I didn't think about, of course. And if you don't have G++11, you can put the name you want here. So I give you the, yeah, I give you the symmetrist. If I do something like this, normally Discord will not bother me with stupid stuff. Yeah. So you can go inside it and put the compiler you want, or you can also, since it's a different compiler, you can use the CUDA CXS compiler. Yeah, of course, if you want. I thought we have a bit of time.
Can type is not specify the version?
If you can type G++ and you have a link somewhere, normally it should be okay.
My version with G++ is 11.5.
Yeah, but if you use 11, normally it should be okay.
I can replace by 11.5.0.
It's not working with 11?
No, I had it.
Maybe, or maybe you have to specify the full path because maybe your compiler is not in a classical install. Yeah, yeah.
In the CUDA selected.
Yeah.
Okay. So CUDA host compiler and I think
I will finish and then we will have some questions if you have. So in terms of computing, so we can compute and do the transfer in another stream as we already did. For example, in this here, we do all the transfer here and then the compute, and then if I do here, then we have some transfer here. So it's not really efficient, but it's simple. And we can also say, okay, but let's compute everything and do the transfer after. It's also possible. Or you can say, okay, I want to compute and then transfer and compute another stuff and during the transfer of the other stuff. And here, so we can do that in this example. We will not gain much because we have a lot of computation, but we can gain a bit. And we want also to avoid this kind of issue because if we do not have enough computation, we will not overlap the transfer with the computation, and so we are an IO1 in that case. Okay. No, we don't have time for this one. So we can also have a completely asynchronous computation. So we will have it in the examples once I will merge the correction. So the idea is once you see this kind of color in Nsight, you want to be happy because this is the only way you can have real asynchronous transfer. So if you want to use CUDA memcopy async, you must use CUDA malloc host and CUDA free host to allocate your host tables and pointers. Otherwise, you will not get this this pink and light green value, but the classical red and green. And this is to tell you that the page is spin. So the access is faster, and so the access can be asynchronous. And then you can use CUDA memcopy async, and you can use your kernel. You specify your grid, your block, the shared memory if you want to use them, and the stream, and then the parameter. So if you don't get this kind of color in Nsight and you want to have something asynchronous, you missed the pin, a priori you missed the pin allocation. So you need to use a CUDA malloc host for that. Oh yeah, the last one. So I told you about CUDA graph, so I don't want to bother you now because it's a bit tricky, but what we can say is to tell, okay, we want to compute U and V images. We can use a graph. So we can express concurrency even if maybe we cannot have it because of the 100% usage of the occupancy. And then we loop, and then we do all the images like this. And as I told you before, now we can also improve that and say, okay, we can have a while inside the graph to repeat all the call on the GPU without any transfer, any way to launch a kernel, and then get all the images at the end. So I don't have a fully working one here because the documentation is horrible. But this one is already, you have several examples with this one in the examples. And to finish, so by doing all of this, so we start, if you want to do the full computation, so for my F3000, for example, I start from 12 seconds with the really bad implementation with all the wrong rows and wrong column, and I end to 4.1 seconds. Last year I was stuck in 5.1, so it's 1 second improvement in 1 year compared to last time. And you have to take care about everything. So data ordering, the block size, do I have contiguous data over my x-axis? How much warp can you have in flight at the same time in your streaming processor? The number of threads you want to start. By the way, if you look at the Nsight, you will see that here, for the CUDA part, we get our HD thread, if you want. So we have 2 million threads here, 1 thread per pixel. And if you spy Nsight with NVC++ with Nsight, you will see that this is 1 million. So each thread is computing 2 pixels, not only 1. So it's possible. And maybe if at the end, just forgot, at the end, you may want to do some kernel fusion because, of course, the Grace code is really small, as you might see. So you have the STD part here. So if I do some kernel fusion, I have only 1 kernel to call. So here, the first one with all the speculative prefetch and all the program that goes with it. And here, I have a much faster kernel. So it's 133 microseconds with this kernel. So I said, okay, Laplacian plus the other Laplacian plus the computing of the update is too costly. The kernel is too small. So the time we spend to start them, even with the graph, is too big. The kernel are really, really small. So let's merge them. So that's why we use kernel fusion. In fact, I start with this one, but it was for the story, it was better to have it in the end. So this one has an occupancy of 83% because of the overhead of thrust. And if I find only I should have this one normally should be quite practically quite okay. We can get normally better performances. No, it's the older. Fusion, this one. Okay, of course. I have too many. You notice that I have too many profiles in my Nsight, of course. I use it a lot. It's a really good tool. And here. So I spy NVC++, and I reach 100% occupancy with a fused kernel. So the kernel to do the full computation. So that's why I get the 4-second runtime. So as I already said in my webinar, I really use NVC++ like this. So I start simply with NVC++, and then I learn from it, and I try with CUDA to improve it. And then you can get rid of the overhead of thrust if you need to get rid of the overhead, because otherwise it's really nice to have it. We had it in fact in the analysis for just for fun at the end, and it's really, really powerful. So depend of what you want to do. Yeah, you want also to get the block shape, really important. So the warp, the size of the warp, the occupancy, the number of threads, the data transfer, the asynchronism, but it's quite difficult also, and check as much as you can this check. So if you want to have the correction, I just have to merge to do, and you will have too much example, because I think there is maybe more than 20 examples in this, just on the CUDA part, if you want to play with, or with graph, without graphs, with the asynchronism, with it. So as you want. So if you have some question, we still have 5 minutes before the talk of Vincent, so don't hesitate.